I want to talk about rate of chemical reactions, the speed in which the reactants turn into products. But how can we measure this rate of chemical reactions? Let's go ahead and take a look. We have reactions such as rusting, which can take years and even decades, and our usual reactions like the one between magnesium and zinc, right? And then in the extreme end, we have things like fireworks that take a split of a second, a fraction of a second to occur. In layman terms, the rate of reaction is how fast the reactants are being used or how fast the products are being formed. That's what we mean when we say rate of chemical reactions in the day-to-day language. So we say that the rate of reaction is equals to the quantity of reactants used divided by the time taken, or the rate of reaction is equals to the quantity of products formed divided by the time taken. That can be in grams and sometimes centimeter cube. But what is the prerequisite for a reaction? When can we say a reaction has taken place? Let's take a look at the collision theory. We use the collision theory to explain how chemical reactions occur and why reactions differ for different reactions. It states that for a reaction to occur, the reactant particles must, one, collide, right? So we need a collision between the particles in order for a chemical reaction to occur. Not only do they need to collide, they need to collide while having enough energy, right? Well, maybe you can ask, what constitutes as enough energy? Is energy that is equals to or greater than the activation energy for that reaction. Remember grade 11, we talk about activation energy and reactions. So right, we are building up from that. We need these particles to collide, and then as they collide, they must have energy that is greater or equals to the activation energy for that particular reaction. And then the last thing that needs to occur is that they need the right orientation at the moment of impact. They don't just only need to collide with sufficient energy. They need to collide sufficient energy and then they have the right orientation for a chemical reaction to take place. Right, so that is the collision theory. It explains to us how chemical reactions occur. So let's go ahead and take a look at factors that affect the rate of a reaction. The first thing that we're going to talk about is temperature. So think about those 3 points under collision theory that we say needed to occur or we need to meet in order for a chemical reaction to occur. Well, we need enough energy, a collision, and the right orientation. So think about temperature. When you increase the temperature, what are you increasing? You're increasing the average kinetic energy of the particles, right? So obviously that will have an impact on the rate of reaction per the collision theory. So let's take a look. Higher temperature increases kinetic energy of particles. Makes sense because we define temperature as the average kinetic energy of the particles, right? So let's take a look at what the collision theory says. Therefore, more molecules have enough or sufficient kinetic energy when the temperature is increased, because the temperature increases the kinetic energy of the particles. So more molecules will have kinetic energy equal to or higher than the activation energy. And as a consequence, if we have more molecules that have enough kinetic energy greater or equal to the activation energy, we are going to have more effective collisions per unit time, and then as a consequence the rate of reaction increases. So when you increase the temperature, the rate of reaction increases. Why does it increase? It's these 3 points that you're looking for. More molecules will have sufficient kinetic energy that is equals to or greater than the activation energies, and as a consequence we're going to have more effective collisions per unit time, right? You can see in the diagram provided that when the temperature is low, there isn't a lot of movement, there isn't a lot of kinetic energy in the particles. But when you increase the temperature, there's a lot of movement, there's a lot of collisions, therefore, as a consequence, right? So that is how temperature affects the rate of a reaction. Okay, and then the graph that we're seeing in front of us, what is that all about? So this graph is the Maxwell-Boltzmann distribution curve, okay? It shows you the kinetic energy on the x-axis and the number of molecules on the y-axis, right? This is how the distribution of energies looks like throughout the molecules in a substance. But take a look at this. When we increase the temperature, we get this graph that is represented by y. We get that line that is represented by y. How does the line represented by y differ from the line written x? In y, the peak of the graph goes down, right, as you can clearly see, and then it shifts to the right. It shifts to the right. Most particles had low kinetic energy, but when we increase the temperature, you can see that most particles have more kinetic energy. So let's say, for instance, the activation energy for this reaction was somewhere here. Let me just erase that. Let's say the activation energy was somewhere here. You can see that in X, the area under the graph is much smaller than the area under the graph of Y, right? So clearly, we're going to have more particles that have energy equals to or greater than the activation energy, right? The area under the graph, as far as the activation energy is concerned, will be much greater when the temperature is increased compared to before it is increased. What I want us to talk about next is the concentration. How does the concentration affect the rate of reaction? We must still be thinking along the lines of the collision theory. Remember, we need a collision, enough kinetic energy, the right orientation. So how does concentration affect any of those three? Let's take a look. Increasing the concentration increases the number of moles per unit volume. Correct, because we know that concentration is equal to the number of moles divided by volume. So when you increase the concentration, you're increasing the number of moles per unit volume, right? So the collision theory, more molecules have enough or sufficient kinetic energy. More molecules have kinetic energy equal to or higher than the activation energy. And lastly, more effective collisions per unit time. Why is that the case? Take a look at A. You can tell that we don't have a lot of particles in A compared to a lot of particles in B, right? But obviously, when you take a look at B, because we have more particles in a very small volume, there's going to be a lot of collisions in there because we have more moles per unit volume, right? They are most likely to collide versus when we have a lower concentration versus when we have a very high volume and the number of moles is very small, right? So concentration increases the rate of reaction because when you increase the concentration, you're increasing the number of moles themselves per unit volume. So they are most likely to collide because there is more of the particles, right? There's just no way around that. They are most likely to collide. So that is concentration. That is how it affects the rate of reaction. Let's take a look at the Maxwell-Boltzmann distribution curve and see how that looks like. We still have the kinetic energy on the x-axis. We have the number of molecules on the y-axis. But you can take a look at C1 before the concentration is increased and take a look at C2 after the concentration is increased. You can see clearly that you can see the graphs here. They've been shown clearly that there are more moles present at C2, meaning more have required activation energy and are able to react, right? There's more moles under the graph C2 when the concentration has been increased. So we're going to have more molecules with EK greater or equals to the activation energy, and consequently more effective collisions per unit time, and the rate of reaction increases. So you increase the temperature, rate of reaction increases. You increase the concentration, rate of reaction increases. And then when you increase the pressure, the rate of reaction also increases. Let's take a look. So increasing the pressure increases the number of molecules per unit volume, right? Very close to how concentration works. Even though here with pressure, you're not increasing the number of moles, you are decreasing the volume, right? As you can clearly see on the sketch that is shown, we are not increasing the number of moles here, we are decreasing the volume. When we decrease the volume, we have that same number of moles, but now in a very small space, right? In a very small container, so to say. So they will be most likely to collide because they are in a very small volume. They're in a very low volume compared to when they are, let's say this is A, compared to when they are in A, right? In B, they are most likely to collide because that is very small. So what does the collision theory say? More molecules have enough or sufficient kinetic energy. More molecules have kinetic energy equal to or higher than the activation energy. More effective collisions per unit time. Let's talk about surface area. That is another thing that affects the rate of reaction. We usually talk about surface area a lot in exams and so on. Let's hear what it says. So increasing the surface area increases the number of molecules that are ready to react, right? That is the main point. That is the point that we need to understand, because everything after that is just the same. When molecules have enough kinetic energy, EK greater than or equals to the activation energy, more effective collisions per unit time. The main point is that increasing the surface area increases the number of molecules that are ready to react. So let's explain what that means. I think we can all agree that if you cut food into smaller pieces, the food tends to cook faster, right? We can all agree. But why is that the case? Why does the food cook faster when it is cut into small pieces? It cooks faster because you've increased the surface area, increasing the number of molecules that are ready to react. So your rate of reaction increases, which in turn the food cooks faster. Let's take a look at the nature of reactants. Substances have different chemical properties and therefore react differently and at different rates. We've talked about that at the very start. The rusting of iron, right, versus fireworks. That is based on the nature of reactants, right? If you increase the temperature of an iron by 5 degrees Celsius, it doesn't really affect its rusting process. The last factor that affects the rate of reaction is a catalyst. The catalyst provides an alternative route of lower activation energy. It provides an alternative route of lower activation energy, right? And then because now the activation energy has been lowered, more molecules have sufficient kinetic energy. That is, the kinetic energy is equals to or greater than the activation energy, and the more effective collisions per unit time will therefore occur. Okay, so the Maxwell-Boltzmann distribution curve, let's take a look at it. So I've extracted this from a past exam question. This is like part of the memo. That's why it says making a criteria here. So take a look at this. Point X is the lower activation energy provided by the addition of a catalyst. So this is where the activation energy was located. But after the addition of a catalyst, point X, that's the lower activation energy, right? So because the activation energy has been lowered, more particles will have kinetic energy that is sufficient to make a reaction, right? A fruitful reaction, a fruitful chemical reaction, an effective collision, and hence the rate of reaction increases. We have just talked about the factors that affect the rate of a reaction. Now let's talk about different ways in which the rate of reaction can be measured. So in grade 12, more especially rate of reactions and chemical equilibrium, you're going to come across a lot of experiments, right? The questions that you're going to be answering will be based usually on experiments. So I'm about to show you different kinds of setups that you can expect as far as the rate of reaction is concerned. So let's take a look at the first setup. The volume of gas produced in a reaction may be measured by collecting the gas in a gas syringe. So take a look at this setup. We have the reactants, and on top of the conical flask, we have a gas syringe. So this setup will obviously work in a reaction where a gas is produced, right? So as more gas is produced, the plunger is pushed out and the volume of the gas in the syringe can be recorded. By measuring the volume at set time intervals, we can graph the data and hence determine the rate of a reaction, right? So this is the graph you would expect after you have measured the gas produced at set time interval using a gas syringe system, right? So as gas is produced and it's leaving the conical flask into the gas syringe, this part is going to be pushed out. This is the plunger, right? And then you can see these lines here. They will allow us to calculate the volume of gas produced. And then with the volume of gas produced and the given time intervals that we know, we can be able to calculate the rate of a reaction. This is the graph you would expect. So obviously at the start of the reaction, there is 0 centimeter cube of gas produced. But then as the reaction proceeds, gas is produced and then it fills it, and then it starts to fill the syringe. So at the very start of the reaction, we expect a steep gradient because that's where the reaction is at its fastest. And then as the reaction proceeds, the gradient decreases. And then ultimately, at the end of the reaction, we expect our line to be flat, showing that the reaction has stopped. There is no more gas that is being produced. Another technique we can use to measure the rate of a reaction is to calculate the change in mass, or measure rather, as you can see the setup. So for a reaction that produces gas, the mass of the reaction vessel can be measured over time. The mass loss indicates the amount of gas that has been produced and escaped from the reaction vessel. If the reaction vessel is sealed, this method will not work. So take a look at this. You take your conical flask, you put it on a scale, right? And then you put a cotton wool to allow gas to escape and not liquid. So because there's a cotton wool on the top, the gas will be able to escape, but everything else remain in the conical flask, right? So the decrease in mass will give you the amount of gas that is escaped. Because if there's gas that is being produced and you only have a cotton wool at the top, the gas is gonna leave the conical flask through the cotton wool. So the mass is gonna decrease. But then that decrease in mass, we can therefore use it to calculate the rate of a reaction. But obviously, if the reaction vessel is sealed at the top, this will not work. And lastly, there's reactions where a precipitate is formed. So in reactions where there's a precipitate, the amount of precipitate formed in a period of time can be used as a measure of the reaction rate. For example, when sodium thiosulfide reacts with an acid, a yellow precipitate of sulfur is formed, as you can clearly see in our reaction. So take a look at this. Take a look at the setup. So we have the reaction vessel, right, on top of a paper that has an X on it. There's a marking there on top of the paper. So from the top, right, looking down in the reactants, you can see the X clearly at the bottom of the reaction vessel. But then as the reaction proceeds and this sulfur precipitate is formed, it will cover the marking at the bottom of the vessel. You can see how it looks without the precipitate before it is formed. But after it is formed, then you're no longer going to see the cross. You can see that it is covered. So that is another technique that you can use to actually measure the rate of reaction. So expect to find this kind of setups in the exams and so on, but not only limited to these ones. The following reaction takes place, and after 2 minutes, 4 grams of lithium has been used. Calculate the rate of the reaction. So, there's different ways in which we can calculate the rate of a reaction. We can calculate the rate of a reaction using the mass, number of moles, volume, or concentration. Usually, the question is going to tell you which unit you need to use. But in our case, we are given the mass. So we can go ahead and calculate the rate of reaction using the mass. But because we can easily convert mass to number of moles, let's also do it using the number of moles. Let me show you how. So the first thing that you're going to do, rate of reaction is equals to. So what information are we given? We are given the mass of lithium that has been used. So because lithium is the reactant, we are going to say that the rate of reaction is equals to minus the change in the mass of lithium divided by the change in time. Why is there a minus sign? I'm putting that minus sign because it is the rate of reaction that you're calculating using the reactant. So the change in mass will be negative. So when I put the negative sign there, it ensures that my answer will be positive. If I was given information regarding one of the products, then I was just gonna say the rate of reaction is equals to the change in mass divided by the change in time, because the change in mass would be positive given the mass of the product. So here the rate of reaction is going to be equals to minus mass final minus mass initial, right? That is what we imply by the change in mass. So after 2 minutes, 4 grams of lithium has been used. So we can say that now we have 0 as the final, and the initial we have is 4 grams, right? And then we divide that by the change in time. So this is happening over the course of 2 minutes. But obviously we know that the SI unit is seconds when it comes to time. So we're going to say 2 multiplied by 60. We are converting that 2 minutes to seconds. So now it's just a matter of me substituting that in my calculator. So let me go ahead and do that and see what I get. This is 0.033 grams per second. There we go. 0.33 grams per second. That is the rate of reaction when we are using the mass. If the question was specific and saying, let's calculate the rate of reaction in moles per second, we would therefore say, okay, it's fine. The mass that we have, the change in mass is 4 grams, right? So the mass is equals to 4 grams. So let's use this mass to find the number of moles. The number of moles using the mass obviously is equals to the mass divided by the molar mass. So the mass is 4 grams and the molar mass of lithium is 7. So that is 4 divided by 7. Let me just put that in my calculator. .5714. Right. So before you get to the final answer, you want to round off to 4 decimal places. And only when you get to the final answer will you round off to 2 decimal places. So there we go. We have the number of moles of lithium, right, that we used in that 2 minutes. So now we can go ahead and say that the rate of reaction will be equals to minus the change in the number of moles divided by the change in time. So the rate of reaction is going to be equals to minus the change in the number of moles is supposed to be minus 0.5714. Right. The time is still the same, 2 minutes. So we're going to have 2 multiplied by 60. So let me substitute that in my calculator. 0.5714 divided by 120. This is equals to 0.0048 moles per second. There we go. This would be the rate of reaction in moles per second. And what we calculated here above would be the rate of reaction in grams per second. Right. In the exam, most of the time, the question will be specific. Calculate the rate of reaction in terms of grams per second, in terms of moles per second, so on and so on. So this is just the very first example. Quite easy, straightforward, nothing complicated. Let's take a look at the example that follows. Right. So 5 grams of zinc pieces are added to 400 centimeter cube of 0.5 mole per decimeter cube hydrochloric acid. To investigate the average rate of the reaction, the change in the mass of the flask containing the zinc and the acid is measured by placing the flask on a direct reading scale. The reading on the balance shows that there is a decrease in mass during the reaction. The reaction which takes place is given by the following equation. There we go, we have the equation. So you can see that this setup, what is going on here, is one of those situations that we talked about when under measuring the rate of a reaction, that you can place your conical flask or whatever you're using, whatever contains the reactants, on top of a scale, and then that decrease in mass can therefore be used to calculate the rate of reaction. But anyway, stories. Let's take a look at the first question. A. Why is there a decrease in mass during the reaction? Right. So, like we talked about, that method only works if there's a gas produced, because you put your reaction mixture on top of a scale, and then as the gas is produced, it's going to escape. So there's going to be a decrease in mass, and that decrease in mass is going to give you the amount of gas that is actually produced. So why is there a decrease in mass during the reaction? Because this hydrogen gas is going to be escaping the vessel, the conical flask, whatever we're using to carry out our experiment. So that is the answer to A. Why is there a decrease in mass during the reaction? The gas that is produced is going to escape the reaction mixture. All right. So that is the answer to A. Let's take a look at the answer. Let's take a look at B. The experiment is repeated, this time using 5 gram of powdered zinc instead of pieces of zinc. How will this influence the rate of the reaction? Another conceptual question. Obviously, the rate of reaction is going to increase if we use powdered zinc instead of pieces. Why? Collision theory. We talked about this. If you use powder instead of pieces, you increase the surface area. So there is more number of moles that are exposed and ready to react. So more particles are going to have enough kinetic energy. What do we mean by that? Kinetic energy that is equals to or greater than the activation energy. More effective collisions per unit time, rate of reaction increases. That is the answer to B. Quite basic, it's just the concepts that we have went through. So that is A, B. What about C? Let's take a look at C. The experiment is repeated once more, this time using 5 grams of zinc pieces and 600 centimeter cube of 0.5 mole per decimeter cube hydrochloric acid. How does the average rate of this reaction compare with the original reaction rate? The experiment is repeated once more, this time using 5 grams of zinc pieces and 600 centimeter cube of 0.5 mole per decimeter cube hydrochloric acid. How does the average rate of this reaction compare with the original reaction rate? So what is the difference? The concentration of the hydrochloric acid is still the same. What has changed is the volume. Initially, the volume was 400 centimeter cube, and now the volume is 600 centimeter cube. If you remember, the factors that affect the rate of reaction, there is no way where we talked about the volume. We only talked about the pressure. And when we were talking about the pressure, it was in relation to gases. In this situation, where the concentration is still the same, the rate of reaction will remain the same. It is not going to increase or decrease. But the reaction might go on for longer because we have more number of moles. But ultimately, the number of moles per unit volume is still the same because the concentration has not changed. So the rate of reaction when we've increased the volume to 600 centimeter cube will be the same to our initial conditions where the volume is 400 centimeter cube. That is C. Let's take a look at D. What effect will the catalyst have on the average rate of this reaction? So obviously, the catalyst will provide an alternative path, an alternative route of lower activation energy. And the more molecules, more particles will have sufficient kinetic energy. So we expect the rate of reaction to therefore increase in this situation. Right. So these were the conceptual questions. I hope you got most of them right, and you can still remember the section on factors that affect the rate of reaction. Well, let's move to the following example. Right. So 5 grams of calcium carbonate powder reacts with 20 centimeter cube of a 0.1 mole per decimeter cube solution of hydrochloric acid. The gas that is produced at a temperature of 25 degrees Celsius is collected in a gas syringe that are set up and are measuring the rate of reaction. And then the first question, write a balanced chemical equation for this reaction. So let's go ahead and do that. We have calcium carbonate, which is CaCO3 plus HCl, hydrochloric acid. And then this is going to give us CaCl2 plus H2O plus CO2. There we go. Right. And then now we just need to balance our equation by placing 2 here as a coefficient of HCl. So that is the first part of the equation. And then B says that the average rate of the reaction is determined by measuring the volume of gas that is produced in the first minute of the reaction. How will the average rate of the reaction be affected if, Roman figure 1, a lump of calcium carbonate of the same mass is used, right? So in our experiment, we used powder, right? And then our Roman figure 1, they're saying, what happens to the average rate if a lump of calcium carbonate is used? Obviously, the rate of reaction should go down, right? It should be lower as we are using a lump with less surface area, right? And then Roman figure number 2, 20 centimeter cube of 0.2 mole per decimeter cube of hydrochloric acid is chosen. So think about the last question. We said that the concentration has remained the same. The last question, I mean this one right here, right? We said that the concentration has remained the same. What has changed is the volume. We have more volume now, but the rate of reaction will remain the same. But in this situation, the volume have remained the same, but the concentration has increased. We have more number of moles per unit volume. So the average rate will actually increase in this situation because even though the volume has remained the same, the concentration has increased. We have more moles per decimeter cube. But in the previous question, the volume had increased, but we still had the same number of moles per unit volume, per decimeter cube. Right. So I hope you can see the difference there. Okay. The following question. Consider the following reaction and calculate the reaction rates for the situations that follow. The first question A, Roman figure 1.35 mole of N2O5 is used and the reaction goes to completion in 30 minutes. Okay, we're supposed to calculate the rate of reaction there. Obviously, we can do that in two ways. We can just use the number of moles that are given, or we can convert the number of moles to mass and actually use the mass. But it's preference at this point. We can use whatever we want to use. Okay, so let's go ahead and do that. Roman figure 1, we are supposed to calculate the reaction rate. Okay, so rate of reaction. What information are we given? Are we given the products or are we given the reactants? We're given the reactants, so we're supposed to have a minus sign, right? So minus the change in the number of moles of N2O5 divided by the change in time. So this is going to be equals to minus 0 minus 1.35. Everything divided by the time taken. So the reaction goes to completion in 30 minutes, right? So we're supposed to have 30 multiplied by 60 because we want to convert that 30 minutes to seconds. So 1.35 divided by 30 multiplied by 60. This is equals to 0.00075 moles per second. Okay, there we go. That is the average. That is the rate of reaction in Roman figure 1. Let's take a look at Roman figure 2. Roman figure 2, the rate of reaction. So let's take a look at the information. We have 2.7 moles that are used, and they are used up in 60 minutes. Okay, so minus change in number of moles divided by change in time. This is going to be equals to minus 0 minus 2.7, right? 2.7 divided by 60 minutes. So that is 60 multiplied by 60. So substituting that in my calculator, I have 2.7 divided by 60 multiplied by 60. And then this is equals to 0.00075 moles per second. Right. So these are just the basics. We're just trying to get ourselves comfortable with calculating a rate of reaction and answering these conceptual questions. Let's take it a step further. Let's see how difficult it can get. But rest assured, we are going to be able to do it. Let's go ahead and take a look.
It is actually easy to see that the forward reaction is endothermic. The energy of the products is greater than the energy of the reactants. So the answer to 5.1.1, our reaction is endothermic. 5.1.2, calculate the heat of reaction for the forward reaction. So what is the heat of reaction, or the enthalpy change? Is the energy of the products minus the energy of the reactants. Let's look at the energy of the products first. Our products have an energy of 420 kilojoules per mole, while the reactants start with an energy of 0 kilojoules per mole. So our enthalpy change will be 420 minus 0, which is just equals to 420 kilojoules per mole. That is the answer to 5.1.2. Looking at 5.1.3, write down the activation energy for the reverse reaction. Now we are interested in the activation energy for the reverse reaction. So the activation energy for the reverse reaction will be this energy here at peak, which is 480 kilojoules per mole, minus the potential energy of our reactants. For the reverse reaction, that will be 420 kilojoules per mole. So we have the activation energy being equals to 480 minus 420, which is equals to 60 kilojoules per mole. Right, that is the answer to 5.1.3. Let's look at 5.2. The following graph represents the number of particles against a specific amount of kinetic energy of the molecules. The data for samples R and S was obtained at different temperatures, which affects the rate of reaction. There we have our graph for R and S. We have the number of particles on the y-axis and the kinetic energy of the particles on the x-axis. The first question, 5.2.1, is asking us to define the term rate of reaction. That is the change in concentration of the reactants or product per unit time. It is actually that easy. 5.2.2. What does the area to the right of line T represent? Let's go to our graph and see what we have. We have a line T there. So what does this area to the right of line T represent? You should know by now that that area there represents the number of particles. So that is the number of particles with a kinetic energy that is equals to or greater than the activation energy. The number of particles with sufficient energy. That is 5.2.2. Moving to 5.2.3. Which sample was at a higher temperature? Write down only sample R or sample S. So we know that when temperature is increased, more particles will have sufficient kinetic energy. So the graph that has a lot of particles with sufficient kinetic energy was obtained when the temperature was increased. If you look at R, the number of particles with sufficient kinetic energy is given by this graph here. But if you look at S instead, you will realize that not only is it given by that graph for R, but even this portion right here. So we can conclude from that and say that the answer to 5.2.3 is actually sample S. Another way of seeing it is that when temperatures increase, the peak is gonna go down and it is gonna shift to the right, just like what happens with S. Let's move to 5.2.4. 5.2.4. Explain the answer to question 5.2.3 by using the collision theory. So we know fully well that when the temperatures increase, the particles will gain kinetic energy. The average kinetic energy of the particles is going to increase. And then more particles will have sufficient kinetic energy. That is the kinetic energy that is equal to or greater than the activation energy. So the area under the graph to the right of line T should increase, just like we saw with sample S. 5.3. In 5.3, the question is saying that 11 grams of magnesium ribbon reacts with a 0.25 moles per decimeter cube of hydrochloric acid solution at a temperature of 25 degrees Celsius according to the following balance reaction. There we have it. A table of the results is given below. The first question, use the graph paper that is printed on the last page of the question paper and plot a graph for this result. So even though we don't have a graph paper, let's see what we can do here. So we have our y-axis and we have our x-axis. On our x-axis, we're going to have the time, obviously. So let's have an interval of 1. So we're going to have 1, 2, 3. And then on the x-axis, that is time in seconds. And then on the y-axis, we have the volume. We have the volume in centimeter cube. Right. And then we have 0 to 35. So let's move with an interval of 10. So let's say 1, 2, 3, 4. Those 4 blocks will give us 10. So we have 10 and then 1, 2, 3, 4. Let's have 20. 1, 2, 3, 4. Let's have 30. And then 1, 2. Let's say that is 35. Right. So our first coordinate, we have 0 and 0. So let's just put a bullet point here. And then we have 0.5 and 17. So 0.5 and 17 somewhere here. We have another bullet point right there. 1 and 25. So we have 1 and 25 somewhere here. 1.5 and 30. So midway between 1 and 2 and 30. So something like that. And then 33 and 2. So 33 and 2. 35 and 2.5. 35 and 2.5. And again, 3 and 35. So we should have something like that. 5.30.2. Use the graph paper and explain what happened with the reaction between 2 minutes and 3 minutes. So let's go ahead and look at that. We're interested in 2 and 3. We are interested in 2 and 3. So let's see what happens at that point. You can see clearly that our line flattens out. Our gradient goes to 0. Our reaction is completed. It is no longer taking place. So that's what happens between t is equals to 2 and t is equals to 3 minutes. Actually, here on the x-axis, it's actually not seconds, but minutes, right? 5.3.3. So in 5.3.3, the question is saying, in a second experiment, the concentration of the hydrochloric acid changed from 0.5 to 1 mole per decimeter cube. Draw a new curve on the same graph paper to show what effect it will have. Label the new curve X. So the concentration of hydrochloric acid has now increased from 0.25 to 1 mole per decimeter cube. So we would expect the rate of reaction to increase. The graph, the new graph that we are supposed to catch, should have a steeper gradient versus the graph we have already, right? So we're expecting something like this. It should have a steeper gradient and it should reach completion before our initial graph. So that's what we're supposed to have. If your graph is below your initial graph, then that is totally wrong. You are saying that the rate of reaction is now decreased, which is not the case. Right, the last question, 5.3.4. Assume that the molar gas volume at 25 degrees Celsius is 24.47 decimeter cube per mole. Calculate the volume of acid that was used in the first experiment when the reaction was completed. So in the first experiment, we have a volume at the end of our reaction, which is 35 centimeter cube of H2, right? So let me just copy again. Let me just copy down that equation again. So we have Mg plus what? Plus 2HCl, and we get MgCl2 plus H2. At the end of our reaction, we have some volume of H2, which is 35 centimeter cube. And we are also given the molar gas volume. So we can use that information to find the number of moles of H2. And then from the number of moles of H2, we can find the number of moles of HCl using the balancing coefficient. The concentration initially is given to us as 0.2 moles per decimeter cube. So it should be easy to actually find the volume like we are asked to do. Let's go ahead and do that. So for H2, we're saying that the number of moles is equals to the volume divided by the molar gas volume. So that will be equals to, so the SI unit for our molar gas volume is in decimeter cube. So we have to convert the volume of H2 to decimeter cube. That will give us 35 divided by 1000, and then everything divided by 24.47. Now it is just a matter of putting that in a calculator to get 1.43 times 10 to the minus 3 moles. Right. So now balancing coefficient, the number of moles of H2 divided by the number of moles of HCl is equals to 1 divided by 2. So the number of moles of HCl will be equals to the number of moles of H2 multiply by 2. And if we do that, we're going to get 2.86 times 10 to the minus 3 moles as the number of moles of HCl. And the last step, concentration, is number of moles divided by the volume. So the volume will be equal to the number of moles divided by the concentration. The number of moles is 2.86 times 10 to the minus 3. The concentration is 0.25. That is 0.011 decimeter cube.
The following apparatus was used by a group of learners in an investigation to find out how surface area affects the rate of reaction between excess solid magnesium ribbon and dilute nitric acid with a concentration of 0.05 mole per decimeter cube. During the reaction, the gas formed is collected in the measuring cylinder. The balance equation for the reaction is given to us right here. The summary of the investigation is tabulated before. So let's take a look. We have experiment 1 and experiment 2, where the mass of magnesium is the same. What is different is the state of division, as we are investigating the effect of surface area. The results for experiment 1 are plotted on the graph below. We can clearly see the graph here where the results are plotted. On the x-axis we have the time, and on the y-axis we have the volume of gas produced. Okay, let's take a look at our equations. The first question, 5.1, besides the mass and the volume of the reactants, give one other variable that must be kept constant during this investigation. Okay, so besides the mass and the volume of the reactants, we also need to keep the temperature constant. So the answer to 5.1 can be temperature. Why do we need to keep the temperature constant? Temperature affects the rate of reaction. So if we don't control the temperature, then your results will not be conclusive. You're not going to know whether your results are influenced by the state of the division or they're influenced by the temperature. So we need to keep all the other variables constant. We need to control them, hence control variable, and then have a fair test. Okay, that is 5.1. What about 5.2? Write down the dependent variable in this investigation. Well, the dependent variable is essentially what we are measuring, right? We are taking a look at the effect of state of division on the rate of reaction. So what you're measuring here is rate of reaction. It is our dependent variable. It is depending on that which is changing the state of division, which is our independent variable. Okay, 5.2. Let's take a look at 5.3. Use the graph to calculate the average rate of the reaction in centimeter cube per second between 2 and 2.5 minutes. Okay, let's go to our graph. So between 2 and 2.5 minutes, 2 minutes is 120 seconds. Okay, so let's take a look. This is 100, this is 150. 1, 2, 3, 4. So one block represents 10 centimeters. Oh, well, 10 seconds, not centimeters. So 1, 2. So 120 seconds should be here. This is where we have 120. 2 to 2.5 minutes. 2.5 minutes, that will be 150 seconds. So it's just 2 minutes plus half of a minute, which is 30 seconds. So 120 and 150 seconds. All right. So let's go ahead and find the corresponding y values. So let's go up. That is 120 seconds, and this is 150 seconds. And then we can extend this line. So that we can read off our value accurately. Okay, we just don't want to use our naked eye here. We want to take accurate measures. So there we go. So the rate of reaction. So rate of reaction will be equals to the change in the volume divided by the change in the time. Right? Why are we using change in the volume? We are given the SI unit we are supposed to use for a rate of reaction is centimeter cube per second. So I'm just respecting that. So let's go ahead and find the gradient. We need to read off these values here. So from 40 to 50 we have 1. We have 1, 2, 3, 4, 5. So it means that one block is 2 units. This will be 42, 44, 46, 48, 50. So it means that here at 120 seconds, we have 42. And at 150 seconds, we have 48. So the change in the volume, we're going to have 48 minus 42 divided by 150 minus 120. Okay, there we go. So let me just put that in my calculator. 48 minus 42 divided by 150 minus 120. That is 0.2. So we have 0.2 centimeter cube per second. There we go. That is the average rate between those 2 points. Okay. That is question 5.3. Let's take a look at 5.4. So 5.4, will the rate of the reaction at 250 seconds be greater than, less than, or equal to the rate of reaction in question 5.3? Give a reason for the answer. So in 250 seconds, it is going to be less than. It is going to be less than. Okay. Why do we say that it is going to be less than? Because as the reaction progresses, of which in our case it is not reversible, as you can see, the amount of reactants gets smaller and smaller. And as we have less number of moles, we're going to have less effective collisions. So we expect the rate of reaction to actually decrease. 5.4. 5.5. Predict how the gradient of the graph for experiment 2 will compare to that of experiment 1. So in experiment 2, we have ribbon as one large piece. And then in experiment 1, we have 5 smaller pieces. So the rate of reaction in experiment 1, we expect it to be higher than that in experiment 2. But what is the question saying? The gradient for the graph for experiment 2, it will decrease. The gradient will decrease in experiment 2 because the rate of reaction will also decrease. And yes, the rate of reaction depends on the gradient. If the gradient is very steep, then the rate of reaction is very high. Okay, that is 5.5. 5.6. 5.6. Calculate the mass of magnesium metal that remains in the conical flask when the reaction is stopped. Assume that the molar volume is 24 decimeter cube per mole. So the molar volume is 24 decimeter cube per mole at room temperature. Okay, fine. Let's go to our equation. Right, our equation, we have magnesium plus HNO3, and then we get in magnesium NO3 2. This 2 is here, it's not there. NO3 2 plus H2. Okay, this is the reaction we have. What is the mass of magnesium that you start with? Because it seems like here we are looking for the mass that is remaining. We start with a mass of 2 grams for both reactions. We start with a mass of 2 grams. So we are bound to use that. So what is the mass of the remaining magnesium at the end of the reaction? How can we possibly do that? Well, we have a graph that shows us the volume of gas produced, right? So what we can do, we can find the number of moles of the gas produced. With the number of moles of the gas produced, we can find the number of moles of magnesium used. With this number of moles of magnesium used, we can find the mass used consequently, and with the mass used and the mass initial that we have, we can find the mass of magnesium that remains. Okay, so these are the steps that we need to take. I keep emphasizing that with this kind of questions, you need your plan fully laid out before you can put pen to paper. Right, everything just becomes extremely simple. You know what you're going to do, when and why. So go ahead and do that. Number of moles of gas produced. We are given our graph, so we need to see where our graph ends here. And can we say that it ends here? I think, yeah, from there on until forever, essentially, our gradient is 0. So we have reached the end of our reaction. So let's take this part. Okay, let's take this part. This is where our reaction ends. Okay, and then we're supposed to extend the line and read off the volume from the graph. So this is the beautiful, well, a beautiful to whom, but this is the interesting thing about these questions. You are always given an experiment, and you are being a scientist. Essentially, you are answering these questions in real time. You've never seen it before, but you have all these skills that you learned, which you need to apply. Okay, so let us see what happens here. Let me join these two lines so that we can read off the value. Okay, I think it will be easy to see here that the volume of gas produced is 60 centimeter cube. Okay, so we will say that number of moles is equals to V divided by Vm. Right, we've said that we're going to do that. We're going to calculate the number of moles of hydrogen gas, of which V is 60 times 10 to the minus 3. That times 10 to the minus 3 converts centimeters to decimeters cubed. I must emphasize, because when you're converting centimeter to decimeter, it's not the same thing as you converting centimeter cube to decimeter cube, right? And then the Vm, it is given to us as 24. Okay, so let's take a look. 60 times 10 to the minus 3 divided by 24. This is 0.0025 moles. So this is the number of moles of the gas produced, hydrogen gas. So now the number of moles of hydrogen gas is to the number of moles of magnesium. We have a 1:1 relationship, right? The balancing coefficients is 1:1. So here, the number of moles of magnesium should also be equals to 0.0025 moles. So there we go. We have the number of moles of magnesium that were used. So we can go ahead and calculate the mass of magnesium. So the mass of magnesium that was used will be the number of moles multiplied by the molar mass. The number of moles is 0.0025. The molar mass of magnesium is 24. So we're going to have multiplied by 24, which is equals to 0.06 grams. So not much of that magnesium was used. So the mass of magnesium that remains will be equals to the mass of magnesium that we started with, 2 grams, minus that which was used, 0.06. So we end up having the mass of magnesium that remains being equals to 1.94 grams. There we go.
Calculate the value of P in the table. So what is the value of P? 0.07, 0.08, 0.09, or you skip the question. Let's find out. So 5.1, we were supposed to define a reaction rate. I'm going to leave that one for you. And the question that follows, 5.2, write down the independent variable for this investigation.
So let's go ahead and read through our question statement and sort of figure out what is happening. The reaction between excess dilute hydrochloric acid and sodium thiosulfate is used to investigate factors that influence the reaction rate. We are given the equation as you can clearly see. The concentration of HCl used is 1 mole per decimeter cube. The same volume of HCl is used in each run. The time taken for the cross on the paper under the flask to become invisible is measured. Okay. The table below summarizes the reaction conditions and the results of the experiment. So, okay, we have the volume of sodium thiosulfate, that of H2O, that of Na2S2O3, the concentration, and the time. 5.2, write down the independent variable. So the independent variable is the variable you are willingly changing, and then the dependent variable is the variable you are measuring. Okay, here we're measuring the time it takes for the cross to be invincible. The variable that you are willingly changing is the volume of sodium thiosulfate. So 5.2, the answer here is volume, the volume of sodium thiosulfate. Okay, Na2S2O3. Okay, so we are willingly changing that volume and we are measuring the time. So we can say that the volume of sodium thiosulfate is our independent variable. Okay, let's take a look at 5.3. 5.3, we're supposed to find the value of P in our table. Okay, that's the determining the value of P is actually not an easy task. Yeah, I had to spend a lot of time trying to figure out. Okay, but then let's pay our attention to run 1. If we pay our attention to run 1, we are given the volume and the concentration. If we were to find the number of moles there, we would have 0.13 multiplied by 50 divided by 1000. Let me put this in my calculator. So 0.13 multiplied by 50 divided by 1000 is 0.0065. So in 50 centimeter cube of sodium thiosulfate, there is 0.0065 moles. How many moles are we going to have? Let's take a look at round 2. In round 2, we're going to have 0.0065 multiplied by 40 divided by 50. This is because now we're no longer using a volume of 50, but a volume of 40. Okay, so 0.0065 multiplied by 40 divided by 50 will give us 0.0052. So these are the number of moles of sodium thiosulfate we have in round 2. To find the concentration in round 2, we would say the concentration is equal to number of moles divided by volume. The number of moles is 0.0052. Okay, the volume is not 40. The volume is still 50 because volume is additive. So 40 plus 10 should give us 50. So we have 50 times 10 to the minus 3. Okay, let me put that in my calculator. When I do that, I get 0.1, just like we have here. Okay, so let's go ahead and determine P. So for P, the number of moles in run 3, we need the number of moles in run 3 first. So those number of moles are going to be equal to 0.0065 multiplied by 30 divided by 50. Okay, so 0.0065 multiplied by 30 divided by 50 will give us 0.0039. So the concentration in reaction, not reaction 3, but run 3 will be number of moles divided by volume. This is 0.0039. The volume is additive. We have 30 plus 20, so that will be 50. Okay, 50 times 10 to the minus 3. That is the same as dividing by 1000. Okay, when I put that in my calculator, I get 0.078. So P should be equal to 0.078. That is the concentration of sodium thiosulfate in run 3. That is 5.3. Let's go ahead and do 5.4. So 5.4, when 0.21 grams of sulfur has formed in run 1, the cross becomes invisible. Calculate the average rate, the average reaction rate with respect to sodium thiosulfate in grams per second. Okay, so we want the reaction rate in grams per second. So that is the change in mass divided by the change in time. Let's take a look at the information we have. For run 1, we're given the time is 20.4 seconds. So we know that delta T is equals to 20.4 seconds. So we're just looking for the change in mass. But we know the number of moles we started with in run 1, right? So in run 1, the number of moles we started with, we calculated it in 5.3. We started with 0.0065 moles. So let's find the mass we started with, so that using this information we have about sulfur, we can find the mass we ended up with, or not the mass we ended up with, but the mass of sulfur that was formed. Okay, so in run 1, the mass, so we're gonna have number of moles is equals to the mass divided by the molar. So the mass will be the number of moles multiplied by the molar mass. Okay, this is the mass we started with, mass initial. The number of moles 0.0065 multiplied by the molar mass. So sodium 23 multiplied by 2 plus, so that is Na2S2. Sulfur is 32, so I have 32 multiplied by 2 plus 16 multiplied by 3. Okay, I already have the answer, but I'm just gonna put it in my calculator once more to verify. Okay, so 23 multiplied by 2, 32 multiplied by 2, 16 multiplied by 3. I'm getting 1.027. 1.027 grams. Initially, I got 1.0478. So I'm just gonna put it back and see where I'm making the mistake. I think this one is the correct one. The one I got initially was wrong. I used 0.0066 instead of 0.0065. Let me see. Yeah, it's 0.0065. So this is the mass initial. This is the mass initial. Okay, we need to be aware of that. So now we know that for sulfur we have a mass of 0.21 grams that is formed. If we convert this mass to number of moles, mass divided by molar, 0.21 divided by 32. So what is 0.21 divided by 32? I'm getting 0.0066. Okay, 0.0066. There's some issue here. Okay, but let's just carry on. How do we move now? We have the number of moles of sulfur that were formed. Okay, 0.0066. With our reaction, let's look at the balancing coefficient. The balancing coefficient of sodium thiosulfate is 1, that of sulfur is 1. So we started with 0.0065 moles of sodium thiosulfate, and 0.0066 of sulfur was formed. Okay, and the balancing coefficient we have 1:1. So the entire sodium thiosulfate was used in reaction 1, not reaction 1, but run 1. Okay, so we know that the mass of sodium thiosulfate goes to 0. So what are we gonna have? We're gonna have the reaction rate being equals to the change in mass divided by the time. The change in mass, we started with a mass of 1.027 and we ended up with a mass of 0 because all number of moles have been converted to sulfur, divided by the change in time, which is 20.4. So let me go ahead and put that in my calculator. I'm getting 0.05 grams per second. Yeah, there we go. That is the reaction rate with respect to sodium thiosulfate. 5.5. Let's take a look at 5.5. Sketch the Maxwell-Boltzmann distribution curve for the reaction at 20 degrees Celsius. Label this curve as A. On the same side of axis, draw the curve that will be obtained at 35 degrees Celsius and label it B. Okay, I think these are easy marks to get. Let me show you why. Because it's the basics. It has nothing to do with this question per se. It's just the basics. Okay, they just want to see if you know what your graphs looks like if temperature is increased. So here we're gonna have the kinetic energy on the x-axis, and then on the y-axis we have the number of molecules. We have the number of molecules on the y-axis. Okay, now we need to increase the temperature. What happens when you increase your temperature? The peak will go down and shift to the left. That's what the examiner is expecting to see, right? The peak goes down and it shifts to the left. So that's exactly what you're supposed to have on your graph, something like this. So it goes down and it shifts to the left, right? Yeah, as you can see, this is A and this is B. B is for 35 degrees Celsius. Yeah, so that's what happens when you increase the temperature. You will have something that looks like that. Yes, we have A and B. Can we move to 5.5? Yes, we can. Explain the effect of temperature on the reaction rate in terms of the collision theory. Okay, we know fully well that when you increase the temperature, the average kinetic energy of the molecules is gonna increase. More molecules are gonna have kinetic energy equals to or greater than the activation energy. More effective collisions per unit time. Rate of reaction increases. Basics.
The reaction of 15 gram of an impure sample of calcium carbonate with excess hydrochloric acid of concentration 1 mole per decimeter cube is used to investigate the rate of a reaction. And then we're given the balanced equation for the reaction. And then it goes on to say that the volume of CO2 produced is measured at regular intervals. And then we have the sketch with the volume of the CO2 on the y-axis and the time on the x-axis. And then the first question, 5.1, says define the term reaction rate. We know that the reaction rate is the change in concentration of the products per unit time. The change in concentration of the products per unit time, or the change in concentration of the reactants per unit time. So that is given by the reaction rate equals to the change in the concentration of the products per unit time, or the change in the concentration of the reactants per unit time. I hope you get that. And then 5.2 says, give a reason why the gradient of the graph decreases between T2 and T3. This is the part we're talking about that I just highlighted in yellow on the left hand side. The question is saying, give a reason why the gradient of the graph decreases between T2 and T3. Because now we are T2 and we're going to T3, the amount of the reactants is getting depleted, right? So from T2 to T3, the gradient is decreasing because the amount of the reactants is getting depleted and the reaction rate is going down, right? So the amount is getting, the amount of the reactants is getting depleted, and as a consequence
the reaction rate is going down. And then we can move to 5.3. We have 5.3.1, and then it says changes in the graph between T1 and T2 are due to temperature changes within the reaction mixture. And then 5.3.1 says, is the reaction exothermic or endothermic? The reaction is exothermic. It's exothermic. Why are we saying that it's exothermic? Because the temperature change is within, right? And then from T1 and T2, the reaction rate increases. Okay, so let me go a bit deeper on that and further try and explain the concept. So in an exothermic reaction, there's a temperature change within, right? The temperature within increases. And then we know that if we increase the temperature in a reaction, the reaction rate goes up, right? And then from T1 to T2, we have a very steep gradient, which shows that the reaction rate is high, right? So the only time a reaction mixture will increase its internal temperature, it's if the reaction is exothermic. And then let's move ahead and go to 5.4. 5.4 says the percentage purity of the sample is 82.5%. And then calculate the value of X on the graph, assuming that the gas is collected at 25 degrees Celsius. So we have T equals to 25 degrees Celsius, and the molar gas volume Vm equals to 24,000 centimeter cube. So we're supposed to calculate the volume of CO2 at X. You can see that at X, that's where the graph starts flattening out, right? So what does the graph flattening out tells us? It tells us that at X, the reaction is complete, right? But then we have CO3 calcium carbonate plus 2 HCl, right? We know that the HCl is in excess, so the reaction will complete when the calcium carbonate is depleted. So we cannot use I wrote HC instead of HCl. We cannot use the number of moles of HCl to determine the number of moles of CO2, because the HCl is in excess. Even after the reaction is depleted, we still have HCl. But then we can use the number of moles of calcium carbonate to determine the number of the corresponding moles of CO2 that we're gonna have. And then after we find the number of moles of CO2, we can then convert that to the volume and determine the value of X. So we're going to start by calculating the number of moles of calcium carbonate, because we have the mass, right, and the percentage purity. So the first thing we're going to do, we're going to say that the mass that's reacted is equals to the mass initial multiplied by the percentage purity, right? So that will be equals to, we know that the initial mass is 15 grams multiplied by 82.5%, which is gonna give us, so 15 multiplied by 82.5 percent, that gives me 12.375 grams. So that's the mass of calcium carbonate that reacted. And now I can convert this mass to the number of moles, and then from there I can then find the number of moles of CO2 produced, which I'll therefore be able to find the volume, which is the X we are interested in. So we know that the number of moles equals to the mass divided by the molar mass. What is the mass? The mass is what we just determined right now, which is 12.375 gram, and then we're supposed to find the molar mass of calcium carbonate. So let me pull up my periodic table and see what that leads us to. So for calcium, we have the molar mass of 40, and then for carbon, that's 12, so that's plus 12, and then for oxygen, that is 16, but then we have 3 oxygen atoms, so that's 16 times 3, which is going to be 12,375 divided by 40 plus 12, that's 52, plus 16, 32, 48. So we have 52 plus 48. So we just have 12,375 divided by 100, which is giving me 0.12375 moles, right, of calcium carbonate. And now we can relate the number of moles of calcium carbonate to the number of moles of CO2 using our balanced equation. We know that the number of moles of the calcium carbonate divided by the number of moles of CO2 will be equals to 1 divided by 1, right? 1 being the balancing coefficient in our balanced equation. We can see that we just have 1. We don't have a number, but we know that we have 1 there on calcium carbonate, and then on CO2 it's also true. For the number of moles of calcium carbonate, we say that it's 0.12375 divided by the number of moles of CO2, and then this is just equals to 1 divided by 1, right? So the number of moles of CO2 equals to 0.12375 moles. So now we have determined the number of moles of CO2. We can then find the volume of CO2. But then how do we find the volume? We know that you can determine the number of moles by dividing the volume by the molar gas volume, right? So we have N equals to V divided by Vm. We know what the number of moles is. That's 0.12375 equals to the volume divided by the molar gas volume, which is 24,000. So if we cross multiply the two, we can then determine our volume, the value of X. So we're gonna get V equals to 0.12375 multiplied by 24,000. And then let me put that in my calculator real quick and see what I get. Multiplied by 24,000. That is giving me 2,270 centimeter cube. So the value of X for our equation, that is 2,970 centimeter cube. So let's carry on and do 5.5. 5.5 says, how will the reaction rate change if 15 gram of a pure sample of calcium carbonate? Initially, the mass that was pure was 12.375 grams. Now the mass that is pure is 15 grams. So what will happen to the reaction rate? The reaction rate will increase. And then 5.6 says explain why you say it is increasing using the collision theory. So we know that if the mass increases, we're gonna have more particles, right, that are ready to react. And then with more particles, we'll have more collisions per unit time. And then as a consequence, the rate of the reaction will go up, right, will be high. So that's how you'd explain 5.5. Calcium carbonate is reacting with excess dilute hydrochloric acid, right? And then that is used to investigate one of the factors that affect reaction rate. And then we have some balance equation, right? And then it goes on to say the same mass of calcium carbonate is used in all the experiments, and the temperature of the hydrochloric acid in all experiments is 40 degrees Celsius. And then we have a table there for experiment A, B, C, and then 5.1.1 says, for this investigation, write down the dependent variable. So if you read the question again, you will realize that it says used to investigate one of the factors that affect reaction rate. So the dependent variable here is the reaction rate, because it's what we are investigating, right? The factors that affect the reaction rate. And then 5.1.2 says what is the independent variable. So independent variable is more like, what are we changing to investigate that which we're investigating? If you look at our table, in experiment A, we used granules for calcium carbonate, and then for experiment B we used lumps, and for experiment C we used a powder, right? So the independent variable here is the surface area, because it's what we're changing to determine its effect on reaction rate. And then it goes on to say the carbon dioxide gas CO2 produced during experiment A is collected in a gas syringe. The volume of gas is collected. The volume of gas collected is measured every 20 seconds, and the result obtained as shown in the diagram below. And then we can see the diagram clearly. And then we have 5.2 and 5.2.1. 5.2.1 says what can be deduced from the graph regarding the rate of the reaction during the time interval. And then for 5.2.1 we have 20 seconds to 40 seconds. So let's go and look at this time interval. So from 20 to 40, it starts flattening out, right? It's not really flat, but it's no longer as steep as from 0 to 20. So we can see that reactants are getting used up, right? Are getting used up. And then as a consequence, the reaction rate is decreasing. And then 5.3 says calculate the average rate in centimeter cube per second at which CO2 is produced in the experiment. So for CO2 we are given the volume, right? So our reaction rate will be the change in the volume divided by the change in time. And then we want the average. So when we want the average, we have to consider the entire time interval. If it says between 20 and 40, then we just use the interval 20 and 40. But then it said the average, so we have to use the entire interval. So we're gonna have volume final minus volume initial equals to T final minus T initial. So what is the volume final? The volume final is 500 centimeter cube, right? So we're gonna have 500 minus by 0 because initially it was 0, right? And then we're gonna divide that by T final, which is 60 seconds, and then minus 0 seconds or second, so to say. So let me just punch that in my calculator. So we have 500 divided by 60 in a way, which is 8.33 recurring centimeter cube per second. And then we are done. And then we can move to 5.4, which says, how will the volume of CO2 produced in experiment B compared to that produced in experiment A? Choose from greater than, smaller than, or equal to. This is a tricky question because let's look at experiment A and experiment B, right? So we have the same volume of HCl for A and B, same concentration of HCl, and then instead of granules, they're using lumps, right? So the reaction rates will be different of these two reactions, but then at the end of the day, the volume of CO2 at the end will be the same because it is said that they use the same mass, right? So for one reaction, to be more precise, experiment A, it will complete quicker than experiment B, but then at the end of the day, they're gonna produce the same amount of CO2. So the answer is equal to, right? And then we can move on to 5.5. 5.5 says a graph is now drawn for experiment C on the same set of axes. How will the gradient of this graph compare to the gradient of the graph for experiment A? So this is experiment A, right? And then this is the graph, and they use granules. So experiment C is powder. So we expecting experiment C to shoot up also, right? Let me use a thinner line to also shoot up, but then the reaction ends quicker compared to experiment A, where they're using granules. So our question is asking us about the gradient. So we're gonna say that the gradient will be greater than, right? Which sound a bit weird. It will be greater than in value, but it's not very scientific. It's the gradient will be steeper. Yeah, but then, well, that's what they want from us. So it's greater than. And they're saying that let's back it up using the collision theory. So again, experiment C is powder, right? And experiment A is granules. So basically in experiment C, there is more surface area, and as a result of more surface area, we have more particles that are exposed, and then we'll have more effective collisions per unit time, and as a consequence, the reaction rate will increase, right? And then now we can move to 5.6, which says, assume that the molar gas volume of at 40 degrees Celsius is 25.7 decimeter cube per mole. Calculate the mass of CaCO3 used in experiment 1. So the information we have is information about CO2, right? So if we determine the number of moles of CO2, then we will use the balancing coefficients to determine the number of moles of calcium carbonate and ultimately calculate the mass, right? So we can say the number of moles of CO2 is equal to the volume divided by the molar gas volume. So what is the volume of CO2? Let's check. It's 500 centimeter cube, right? So we're gonna say 500 divided by 1000 convert into decimeter cube, divided by what? By 25.7, like we are told. So we have 0.5 basically divided by 25.7, which is equals to 0.01946 actually moles. So now let's go to our equation. So now we can see that the number of moles of CO2 will be equal to the number of moles of calcium carbonate, right? Because the balancing coefficients are the same. So this will be 0.01946. So the mass will there be for the number of moles multiplied by the molar mass. So we have 0.01946 multiplied by 100. This will give you 1.946 grams.
Two experiments, 1 and 2, are conducted to investigate one of the factors that affects the rate of the reaction of aluminum carbonate with excess hydrochloric acid. And then we have the balance equation there for the reaction on the left hand side. Let me just go ahead and write it down. So just give me a second. Plus 6 HCl is going to give us 2 Al 3 H2O plus 3 CO2. And then we have the setup in the image given there. There we have the hydrochloric acid. I think it's been put in slowly, and then we have the aluminum carbonate at the bottom, and then we have a syringe. So one of the products here is a gas, right? So that means that all the gas that will be released as the reaction is taking place is gonna end up in the syringe. The syringe will be sucking out the gas, right? So we're given some information for experiment 1 and then some information for experiment 2. And then the first question says 5.1, define the term rate of a reaction. That is the change in concentration of the products or reactants per unit time, right? The change in concentration of the products or the reactants per unit time. So formula wise, you write it like this. The rate of the reaction equals to the change in the concentration of the products per unit time. And then 5.2 says, using the experimental setup above, state the measurements that must be made to determine the rate of this reaction. So again, look at the picture on the left hand side. Look at the setup. As I've already stated, one of the products of the reaction is a gas, right? It's a gas. And then the time, you can always measure the time manually, right? So for you to calculate the rate of a reaction, we know that this is we need the change in concentration of the products or the reactants divided by unit time. So one of the things you'll need to measure obviously is delta T, which you measure manually. Maybe you use a stopwatch or something, and then now the change in products or reactants. That's sort of like the trick of this question, because we have this syringe here on the question, on the setup. We are going to measure the volume of the gas that is released. The gas is one of the products, right? So that's how we will use this equation to calculate the rate of this reaction. So the answer will be, we need the time, which we're going to measure manually, and then we need the volume of the gas, right? Volume of the gas, of which we're going to determine from the syringe. Syringes usually they have like what do you call this? They already have markings on them that show the volume and stuff. So you just measure the time, and then the syringe will give you the
the volume of the gas, and then from there you can calculate the reaction rate. Let's move forward. 5.3 says using the collision theory use the collision theory to explain how the average reaction rate in experiment 1 differs from the average rate in experiment 2. So if you pay attention here, in experiment 1 they use a volume of 100 centimeter cube for 1.5 mole per decimeter cube of HCl, and then for experiment 2 they use 50 centimeter cube, and then the concentration is 2 moles per decimeter cube, right, of HCl. So now the question is saying, let's use the collision theory to explain how the average reaction rate in experiment 1 differs from the average reaction rate in experiment 2. So here you can see that here there's less volume, right? Yeah, less volume will mean greater concentration, because concentration is inversely proportional to volume, right? And then here we have more volume. So the rate of reaction of experiment 2 is greater than the rate of reaction of experiment 2. Experiment 2 will take less time because there is more molecules, right? So to put it nicely, the first point you'd say that more HCl particles, right? There will be more HCl particles because the concentration is higher. And then what does more particles give us? More particles give us more effective collisions, right? And then what will more effective collisions give us? More effective collisions. Effective collisions is a prerequisite of a reaction, right? So the more the effective collisions, the higher the reaction rate. So the reaction will take less time. And then I've gone through this on a video I made in the past. I'll put it up here. If it will pop up in the screen, you can click and watch it. Here it is on the top left hand side of the screen. Let's move ahead. On that video I talk about how other factors affect the reaction rate, like the surface area, the pressure of a gas, and all that nice stuff. And then 5.4 says the average rate of the reaction in experiment 2 during the first 2.5 minutes is 4.4. So let's write that we have delta T, which is 2.5 minutes, right? And then we have the average rate of reaction, which is 4.4 times 10 to the minus 3 moles per minute, right? And then the question says calculate the number of moles. So we need the number of moles of what? Let me see, of aluminum carbonate. So that is, let me just write down the formula. Then we have CO3 there, and then we have this 3 there. So we need the number of moles of this aluminum that remains in the flask after 2.5 minutes. So after 2.5 minutes, the reaction is not completed. The question then says, what are the number of moles that are remaining? So, okay, we know that the rate of a reaction is given as the change in the concentration of the products divided by the time it takes. We have the reaction rate, it is given to us. We have the change in time, the time it takes for the reaction to get to our point of interest. And then now, if we can calculate this change, right? This change here,
then we can then be able to calculate the number of moles. But then even if we were not able to do that, is the information we have. We had to start there and then we'd look for, other ways of doing the question. I'm still gonna do more questions on this topic. So if you wanna see more of that and how we tackle different problems, subscribe to the channel and like the video. So, okay, let me move on. The reaction rate, it is said to be 2.5 minutes, and then the change in the product is what we're given. But then if you pay close attention here, aluminum carbonate is actually not the product, but the reactant, right? So here we're supposed to have of the reactant, and then, okay, there we go. Divided by actually I put time where it's not supposed to go. Time is supposed to go here 2.5, and then here we have the reaction rate 4.4 times 10 to the minus 3. That is the same as divided by 1000, right? And then now if you make this reaction, this change in the concentration of R, we get 2.5 multiplied by 4.4, everything divided by 1000. So let me go ahead and put that in my calculator real quick and see what I'm getting. So we have 2.5 multiplied by 4.4 divided by 1000. That is giving me 0.011. So what's the SI unit now? We're getting 0.011, but then what's the SI unit? We know that 2.5 is in minutes, right? And it's been multiplied by the reaction rate, which is in, what's the SI unit? Which is in mole divided by minute, right? So the minute and the minutes cancel out. So the change in the concentration, in the number of moles, is thus 0.011, right? So that's how we are getting to how I'm getting to 0.011 moles instead of moles per decimeter cube. Number of moles in excess equals to, I'm going to explain why I'm doing this in a second, right? Equals to 0.016 minus 0.011, which will give us 0.005 moles in excess, right? So why I'm doing it like this? Let's say you have 8 apples, right? And then here you've eaten 0, and then after some time, now you don't have after some time you've eaten 2 apples, right? So, and then you're like, what's the change in the apples that I had initially? You're going to subtract the number of apples you started with by the change in the apples you eaten. So here you had eaten 0, now you've eaten 2. So you're going to say 5 minus 2, which will give you 3. And then the 3 will be the axis. So the same thing with this question. That's the same idea I'm using. Now let's move to 5.1. 5.1 says calculate the maximum volume. So we have volume of CO2 that can be prepared at a temperature of 25 degrees Celsius in experiment 1. Take molar gas volume at 25 degrees Celsius as 24,000 centimeter cube per moles. Okay, we know that the number of moles can also be given by the volume divided by the molar gas volume. So right, so that is N equals to V divided by Vm. In this question we are given
Vm. The molar gas volume as 24,000 centimeter cube per moles. And then the question says, let's find the maximum volume. So this is what you're interested in. And then what we don't have is the number of moles, right? So if we determine the number of moles, we can then use this formula to calculate the maximum volume of CO2 that can be prepared for experiment 1, right? But then to find the number of moles, it's not really complicated because we can use the equation to do so. We know that in our balanced equation, we have CO2 which is balanced with by 3, right? And then we have aluminum carbonate, which is Al2C CO3, and then we have that 3 on the outside, which is balanced by nothing, which is basically just 1. So what we can do here, this is the number of moles, this is the number of moles. We can calculate the number of moles of CO2, not CO3. I'm sorry for that. We calculate the number of moles of CO2 by cross multiplying. So we're gonna get the number of moles of CO2 equals to 3 multiplied by the number of moles of aluminum carbonate, right? That is 0.016, right? Because the number of moles of aluminum carbonate is 0.016, and then the HCl is in excess. So at the end of the day, all the aluminum carbonate is going to get used up. So this will give us, let me just put that in the calculator real quick. That is going to give us 0.048 moles. So now we have the N we were looking for here. Now we can just calculate V, right? So we're going to say V equals to the number of moles multiplied by the molar gas volume, which is given as 24,000. So we're going to have 0.048 multiplied by 24,000 mole per decimeter cube, right? And then this is the SI unit of this is we have an SI unit of mole for moles, and then here is mole per decimeter cube, right? So moles and mole cancel out. We end up with let me put that in the calculator real quick. 24,000. We end up with 1,152. Am I doing that right? Yeah, 1,152 decimeter cube. Oh no, I just realized that the number. Okay, I wrote this wrong. I just realized that here it is given as a centimeter cube divided by mole, right? So mole and mole cancel out, and then we are left with centimeter cube. 5.1. So we're given a Maxwell-Boltzmann distribution curve for a certain reaction, and then we have Q on our y-axis, we have P on our x-axis, and then we have some point R, right? And then 5.1.1 says P and Q are the labels on the axis. What quantity is represented by P? We know that on the x-axis of the Boltzmann distribution curve, we have kinetic energy, right? So 5.1.1 will be kinetic energy. And then 5.2.2, we are supposed to give the name for Q, which is the number of particles. The number of particles. Yeah, this is the same curves we use when we determine the factors that affect a reaction rate, right? And then if you haven't done that, look at the description. I'll put a link to a video where I was explaining that. And then 5.2 says line R represents the minimum energy required for the reaction to take place. And then 5.2.1 says write down the term of the underlined phrase, minimum energy required for the reaction to take place. That's the activation energy. Activation
energy is self-explanatory because activation, so to say. And then 5.2.2 says, how will the shaded area on the graph be affected when a catalyst is added? Choose from increase, decrease, or remain the same. Now, obviously, it's going to increase, right? Increase. And then I'm going to explain that in a second. Actually, 5.3 asked me to explain why I'm saying it increases. When you had a catalyst, it provides an alternative path, right? So let me just write that down. Alternative path of lower activation energy. So after we have an alternative path of lower activation energy, then more particles will have enough kinetic energy to react, right? Yeah, to react. And as a consequence, we will have more effective collisions. And then, yeah, the reaction rate gets high, right? And then you have your 4 marks. When you add a catalyst, the alternative path, there will be an alternative path of lower activation energy. So particles that previously didn't have enough EK, now they do, and they will form reactions, right? And then the more the number of reactions, the more the number of effective collisions, and then the reaction rate will go up. And then we move ahead to 5.4. So we have a reaction between powdered calcium carbonate and excess hydrochloric acid. It's used to investigate reaction rate at 25 degrees Celsius. And then we have a balanced equation down there. And then several experiments are conducted using the same mass of impure calcium carbonate. And then with different initial concentration of dilute hydrochloric acid. Then the graph represents the results. And then, okay, it is said that we should assume that there are impurities that do not react. Okay, fine. And then 5.4.1 says controlled variable. By control variable, they mean the variable that is constant, is not being changed in any way, right? So if you pay attention to details, when I was reading that statement, it said same mass of calcium carbonate. I just highlighted it in blue on the left hand side. Same mass of impure calcium carbonate. So for 5.4.1, we'll have mass of CaCO3, and then that's the one option you have. And then the other option you have is the temperature, right? They didn't say anything about the temperature, so you can go ahead and see that. And then 5.4.2 it says let's have a conclusion for this investigation. Okay, look at the graph. Look at the x-axis. As the initial concentration of HCl is going up, the average rate of production of CO2 is also going up. And CO2 is our product, right? So that means that concentration is directly proportional to reaction rate. As we increase the concentration of HCl, the average rate of production of CO2 increases. We have more CO2, right? So that means the reaction rate is higher. And then let's move ahead to 5.4.3. It says the calcium carbonate in 6 grams of the impure sample reacts. So we have CaCO3, and then that which is pure is 6 grams, right? And then they're saying that it reacts with HCl, obviously, of concentration 0.03 moles per decimeter cube in 26 minutes. So we have delta T equals to 26 minutes, right? And then 5.4.3 goes on to say, use the information in the graph to calculate the percentage purity of the calcium carbonate. So we want to calculate the mass of the impure calcium carbonate, and then after we do that, we can go back and calculate the percentage purity. Then they say, assume that the molar gas volume at 25 degrees Celsius is V molar gas 24,000 centimeter cube. So, okay, let me just write down the equation down again. So we have calcium carbonate plus 2HCl giving us, okay, let's ignore all the other products and just put CO2, right? Because CO2 is what we're interested in, because that's what we were measuring. So the question is saying, let's calculate the mass of CaCO3, right? And then what do we have? So for CaCO3, we only have the mass of the pure substance, right? And then for 2HCl, what's the information we have for HCl? We only have the concentration. And then for CO2, we have the molar gas volume, we have the average rate, we have the reaction rate, so we have the reaction rate, and then we have the time of the reaction. So it seems like CO2 is what we can use to calculate everything else, because this is where we have the most information. So we can use the reaction rate to calculate the volume of CO2, right? And then after we have used the reaction rate to calculate the volume of CO2, we can use the volume of CO2 to calculate the number of moles of CO2. After we've calculated the number of moles of CO2, we can use the number of moles of CO2 to calculate the number of moles of CaCO3 and ultimately calculate the mass. The thing about this question is that there's no formula I can give you to use in every situation. You have to read the question and understand it, and then you can take it from there. So we know that for a gas, the reaction rate is equal to the change in the volume divided by the change in time. And then if we take this bullet point at the top, where HCl is 0.03, the average rate of production is 50 centimeter cube per minute, right? So we're gonna have 50 equals to the change in volume divided by the change in time. We are told that it takes 26 minutes, so we're gonna have 26 here. And then if we cross multiply, we're gonna get the volume equals to 50 multiplied by 26, which is gonna give us 50 multiplied by 26. That is 1,300 centimeter cube, right? So now we have determined the volume of CO2, like we said. The second step is now to determine the number of moles of CO2. And that is given by number of moles equals to the volume divided by the molar gas volume, which is equals to the volume we just determined is 1,300, and then the molar gas volume is 24,000, right? And that is equals to, so we have 1,300 divided by 24,000, which is given us 0.05417, right, moles. So now we can use the number of moles of CO2 to determine the number of moles of CaCO3 that reacted using the ratio of the balancing coefficient, right? So from our equation, we know that the number of moles of CO3 divided by the number of moles of CaCO3 is equals to 1 divided by 1, right? Because those are the balancing coefficient. So the number of moles of CaCO3 will just be equals to the number of moles of CO2, right? So that will be also 0.05417 moles. So now we've done step 2 to calculate the number of moles of CaCO3. Now we can take a formula and calculate the mass of CaCO3. So we know that the number of moles is also equals to M divided by the molar mass, right? And then we want the mass. So the mass will be equals to the number of moles divided by the molar mass, which is equals to 0.05417 multiplied by, let me check the number of moles of CaCO3. That is 100, right? You can check it on the periodic table. So we're gonna have, let me just put that in the calculator real quick. And then that will be equals to 5.417 grams, right? So now we have the mass of CaCO3 that reacted and the mass of the impure sample, right? So to find percentage purity, we're gonna say percentage purity equals to pure substance divided by impure, right? The whole substance. So this is going to be equals to 5.417 divided by 6, which is, let me just put that in my calculator real quick, which is equals to 0.9027. And then after that, you can just multiply that with 100 so that you get it in percentages. So that will be 0.9027 multiplied by 100. That is 90.27%.